For many problems, we try to use the thin lens approximation. But for this particular problem, since we obviously don't have a thin lens, but more like a spherical lens, we're going to use a spherical lens equation. And the spherical lens equation looks like this. You have the medium of the spherical lens minus the medium of the surrounding environment divided by the radius of that spherical lens equaling to index of refraction of the environment over S plus index of refraction of the lens divided by S prime. And what we have here is just a sign convention where S prime is always going to be positive if on the other side of the lens, and S is going to be positive if on the incident side of the lens. Generally, we say the incident side of the lens is on the left, and then the image part of the lens is on the right. So if you get a negative number for the image, that means the image is going to be on the left, which evidently in this case it will be. So let's go ahead and look at all of the values before we get comfortable plugging things in. So we want to know what the image is first of all. And so let's look at the picture and see where we can find all the other answers. So this is looks like it's a glass sphere. And so for glass, if you look it up, it's about 1.5 index of refraction. Air is 1.0. And it looks like the source is it's a little tricky. So the radius of the sphere is 10 centimeters. And the source is 25 centimeters from the center of the glass. So here's that glass, and the source is 25 centimeters. Now, the problem is with this spherical lens equation, this S defines where the object is relative to the surface or relative to the border. So that's this guy right here, this part. So if this is a 10 centimeter radius sphere and the point of interest is 25 centimeters, then S is going to be 15 centimeters because it's from the border. So that's where it gets a little tricky. That's our first obstacle right there. Okay. And then we have everything else here. Okay, now the second obstacle is when you look at the picture, you're going to see something interesting. You're going to see that it indicates, and greatly so, we're very fortunate for this, it indicates two images. So what's going on is that the source is going to produce one image way back here, and call that I1, and then that image is now the source that produces another image, I2. So you see what's going on there. A source is spewing out light or reflecting light all over the place. The light that interferes with that to produce a clear image goes over here. The light ray goes over here. This then becomes the object of the second image that is then produced over here. And this is the final image, I2. So you can see that the picture already hints to you, you're going to need to use this equation twice. This right here will become the first image, which will then need to be used here so we can get the second image. Okay, so let's go ahead and find the first image and then use that to find the second image. Isolating S prime, we have S prime to be N2 minus N1 divided by R minus N1 over S to the negative first power, and then times N2. Doing the calculation, plugging in all the numbers, you're going to agree that it becomes negative 90 centimeters. And as the picture suggested, the image should be negative because it is right here. It is to the left of this particular border. So negative 90 centimeters from this border is where the first image is. Now that's going to now be used as a source of light for the final and second image. So here's what we're going to do. we're going to go ahead and take this. And we're going to go ahead and find, finally, our last S. And we're going to call it S double prime, just so we can get a little bit of a delineation of values here. So mind you, remember how I said that we conventionally see an object on the one side as a positive number, and then the image is going to be positive if it appears on the other side. Okay, so in this case, the image appeared on the left side, so it's a negative. However, since it's now the object for the second image, we're going to make this a positive number because now it's an object for something else. So S double prime is going to equal to, again, n2 minus n1 over r minus n1 over s prime to the negative first power times n2. Now plugging in all the numbers, and I'm going to go ahead and specify clearly what needs to be plugged in here. This, since it's on the left side of the equation, or sorry, left side of the lens, you're going to now make this a positive 90 centimeters because that's what's convention. Convention is that objects are on the left side, so it's a positive value. So now we put in a 90 instead of a negative 90. You do the calculation, and you're going to agree with me that the image, the final image, is going to be 38.6 centimeters to the right since it's a positive. Okay. Now I would say that that's great. That's a great answer, and we can say that the image location is 38.6 centimeters. Apparently, though, to the reader, we don't know where it's referencing. So the answer, though, to this is like 38.6 centimeters from what? The answer is that same border that we've been working with the whole time. And that's convention, is that it all depends on the one border. So if we want to say how far it is from, say, the center of the sphere, or how far it is from the right edge of the sphere, we'd have to specify that. So let's go ahead and just say, for our purposes, how far it is from the center of the sphere. So we want to know how far from the center of the sphere is. Well, the sphere has a 10 centimeter radius. So what we do is we just take off 10 centimeters from our value, and that's going to give us the image distance from the center. So I'll write down image distance is 28.6 centimeters to the right of the sphere's center. And that's our answer.